Hello class, good afternoon and welcome to today's topic, which is 2.4, determining key features of the graph of a function. So let's start right now. What are the objectives? Basically, we just have one, which is to determine the most important features of the graph of a function, which are divided into these categories. Okay, we're going to talk about the intercepts of the function, or of the graph, sorry. We're going to talk about the symmetries of the graph of the function, and we're going to talk about local and global minima and maxima. Okay, all of these sounds kind of complicated. It's not. It's extremely simple. Okay, because remember what I told you the class before, that the graph of a function is actually very simple to understand because it's visual, and the human being has this capacity to understand visual information very quick, and it's like second nature to us. It's very simple. So all of these things, even though they sound complicated, the concepts are going to be very simple to understand. So let's go into each one of these. So what are the x-intercept and the y-intercept of the graph of a function? Let's read. The x-intercept and the y-intercept are the values at which the graph of the function crosses each axis, respectively. The x-intercepts are also known as the zeros of the function. So very quickly, what does this mean? You have seen this already, right? In some way or another. For example, when we talked about the straight line, we talked about the intercept of the straight line with the y-axis. And this is exactly the same. It works exactly the same. If I have a graph of a function, okay, this is the y-axis, this is the x-axis. Remember that the x-axis helps us plot the values of the independent variable or the argument of the function, and the y-axis helps us or is used to plot the values of the function. Okay, that's why we write this, because the values of the function, which are this, are being plotted in the y-axis. That's why we write this. Okay, so let's draw any graph of any function whatsoever. For example, like I can draw this. Okay, so that's the graph of a certain function f. Okay, so as you can see, this is the graph of a function. Remember, why? Because it passes the vertical line test. That is, if you draw at any point you please, for example, this one, or this one, or this one, or this one, at any point you wish, these red or pink straight lines, which are vertical, only cross the graph at one point. And if that happens, then the graph that is being drawn actually represents a function. Okay, if that doesn't happen, then you don't have a function. These tests have to be passed for a graph to be a function. Okay, so we have this graph of this function. And if you can see, I'm going to go again with pink. If you can see, the graph crosses the y and the x-axis at these points. For example, the x-axis is being crossed at this point, at this point, and at this point. And the y-axis is being crossed at this point. Okay, so let's suppose that the value of this point right here, this precise value on the x-axis is -3. Let's suppose that, okay? And this value is 1, and this value is 4, and this value for the y-axis is 2. Okay? Then we would say the following. The x-intercepts of this graph are -3, 1, and 4. Those are the x-intercepts. And the y-intercept is 2. Okay? The y-intercept. That's what these things mean. It's extremely simple. Okay? That's the idea. We're going to see in a moment how we get them both graphically and analytically. Okay? But that's basically the idea. It's very simple to understand. Oh, and please memorize this. The x-intercepts are also known as the zeros of the function. Okay, memorize that. Memorize that. The x-intercepts are also known as the zeros of the function, because sometimes, very frequently actually, they are referred to as the zeros of the function. Okay, now let's talk about the symmetries of the graph. We have two kinds of symmetries. Symmetry with respect to the y-axis, and in a moment we're going to talk about symmetry with respect to the origin. Again, these are very simple to understand concepts. Concepts very simple to understand. And when we read this in a moment, you're not gonna understand very much what I'm talking about, okay? Because this is the analytical definition, but the visual understanding of this concept is actually extremely simple. So let's read. We say that the graph of f is symmetrical with respect to the y-axis if and only if, remember this part, I'm gonna talk about that part in a moment again, because I'm pretty sure that you forgot by now what this symbol means. It has a very specific symbol. If and only if the following is true: f of x is equal to f of minus x for all x in the domain of f. Okay, all of this sounds very technical. It's not difficult once you understand the concept. Okay, and we also say the following: if f is symmetrical with respect to the y-axis, we say that it is an even function. So any function that is symmetrical with respect to the y-axis, that is, any function that satisfies this requirement, is said to be an even function, una función par. But don't get confused with the concept of even, okay, and odd for the integers, okay, because these concepts are used for integers. For example, an even number is 2 or 4, and an odd integer is 1 and 3. This adjective in the concept of functions do not relate too much to this, okay, so don't get them confused. Okay, an even function has nothing to do with the function being 2 or 4 or something like that. Okay, this is a separate meaning for the words even and odd. Now the symmetry with respect to the origin, the requirement is similar, okay, and we have similar writings for this concept. We say that the graph of f is symmetrical with respect to the origin if and only if the following is true: f of x is equal to minus f of minus x for all x in the domain of f. Again, I keep telling you, try to understand why symbology is useful, okay? Listen to all the words I say. F of x is equal to minus f of minus x for all x in the domain of f. That is a lot of wording, okay? That's a lot of words. And all of those words are comprised very economically into this simple symbolic statement. That's why symbols are good for you. They're not bad. They're not trying to make your life worse. They're trying to help you. Okay, now if a function satisfies this requirement, then we find is symmetrical with respect to the origin, and then we say that it is an odd function. Okay, odd function. But again, not to be confused with anything dealing with odd numbers, okay, like 1 and 3 and 5. Okay, these are separate meanings to the words even and odd. Okay, now let me tell you what this concept means. Symmetry with respect to the y-axis and symmetry with respect to the origin visually. We're talking about graphs. This is a visual these are visual concepts, okay? So let me tell you what it means, and you're gonna understand why this is very simple. So let's go a little to this video and pay attention to this. I'm gonna explain what is happening, okay? So in here I have a function. We have the y-axis, we have the x-axis, and I have a function, okay, which in this case is a parabola. It's a quadratic function. So look at this, and we say that this function is symmetrical with respect to the y-axis for obvious reasons, right? I mean, look at it. This part and this part over here are completely symmetrical if you folded the sheet in half, which I'm about to do. Look, If I folded the sheet in half, you're gonna see that both branches, both sides of the parabola match or overlap. Can you see that? They match. Well, almost. They match. When you fold over the y-axis. Okay, look at that. Both sides match one another. They overlap. Okay, so that's what, let me pause it. That's what symmetry with respect to the y-axis means. That both sides of the graph that are separated by the y-axis, when you fold the graph over the or about the y-axis, those sides are gonna coincide. They're gonna match. They're gonna match perfectly. Okay, like that. They match. Can you see? They match when you fold about the y-axis. So that is symmetry with respect to the y-axis. Now let's go over symmetry with respect to the origin. I'm gonna give you another function. That function, okay? So again, we have the y-axis, we have the x-axis, and we have the graph of a function. What function is this? We don't care, okay? We don't care what function it is at this point. Okay, but it's a function. So this function, or more specifically, the graph of this function is symmetrical with respect to the origin. And visually, what that means is the following. Look at this. I'm just gonna play it for you, and then I want you to try to understand what's happening. Try to understand what's happening right now. Look at the way I fold the sheet. I make two folds now. Okay, so if you didn't get it, let me explain. Okay, so first you're gonna see that I'm gonna fold the graph of the function about the y-axis. Okay, I'm gonna do that right now. There you have it. And as you can see, both branches, which is this branch in here and this branch over here, they don't match. They don't match. Okay, when I did that, they don't match like in the case before. One more time. Okay, they don't match. Okay, that's perfectly clear. They don't match. But if I fold again the sheet now over the x-axis, which is this, can you see? This is the x-axis. If I perform a second fold over the x-axis now, you will see that these two branches now they're gonna coincide. Look, there you have it. Can you see? That is symmetry with respect to the origin. I'm gonna do it again. First, we fold about the y-axis, done. Now about the x-axis, done. And they match. Can you see? That's what symmetry with respect to the origin means visually. Visually. Okay, let's go back to the presentation. What's happening? Okay, now that's what it means visually. Okay, you can actually by just graphing the function, you can see more or less if the function is either symmetrical with respect to the y-axis by just looking at the graph and try to fold it in your mind, you know, and try to see if they match, or you can see whether the graph is symmetrical with respect to the origin by trying to perform in your mind those two folds. First about the y-axis and then about the x-axis. It's a little harder in this case, but it can be done if you have good mental skills. Okay, and that's how you know if they are symmetrical visually. But analytically, how do we know that? We have to perform this test. For symmetry with respect to the y-axis, we have to perform this test, and if this checks, then the function is symmetrical with respect to the y-axis. And for symmetry with respect to the origin, if this checks, if f of x is equal to minus f of minus x, which is a completely analytical method, then we say that the function is symmetrical with respect to the origin. Okay, now let me tell you something a little about this word again, about this symbol in mathematics. I already told you about this symbol. I'm pretty sure most of you forgot by now, and that's to be understood. Okay, these are complicated things to understand, and this is your first introduction to real hardcore mathematics. I'm being very hardcore on you. So what is this? If and only if. All of this symbol is read if and only if. So I'm gonna read this again. We say that the graph of f is symmetrical with respect to the origin if and only if the following is true. Blah, 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 blah. Okay, what does that mean? It means this. It means that this statement, the graph of f is symmetrical with respect to the origin, implies this other statement. Okay? And also backwards. If you have this statement, that if you know that this statement is true, then the first statement is true. Okay? Because remember, when we have two statements, for example, P and Q, the fact that P implies Q doesn't mean necessarily that Q implies P. Okay, I gave you some examples about that. Okay, I can say um, uh, all dogs are animals. Okay, but that doesn't mean that all animals are dogs. Okay, so being a dog implies that okay, let me rephrase it. Something being a dog implies that that something is an animal. I'm gonna repeat that. Something being a dog implies that that something is an animal. Okay, but the inverse, I'm sorry, the converse doesn't apply. Something being an animal doesn't imply that that something is a dog. Okay, okay, can you see? But when you have two statements that actually imply one another, that P implies Q and that Q implies P, then you have this, the if and only if. You can write this in this way: P if and only if Q. And that means that P implies Q and that Q implies P. In other words, they are equivalent statements. And that's what this word means. It means they are equivalent. This statement that I'm underlining right now, this statement implies this. Okay? And this statement also implies this. All of these statements. Okay, they are equivalent. And that's how you represent that in symbols with these little three letters. Okay, if and only if. It's gonna take you some time to get used to this. Okay, don't worry too much. You are learning a new language. And to be honest with you, these things are not taught in normal high schools, okay, or normal programs. You are being taught this because you're IB students, okay. We expect much more from you. At least I do. Okay, and the last concept: local minima and maxima. Let's read. The local minima and local maxima of f are the values of the function which are either a minimum or a maximum in some neighborhood. In some neighborhood of the domain of f. So again, a lot of words. Okay, I need to give you the words. I need to explain them, but the understanding is gonna come in a moment. Okay, so all I want you to memorize is this: for local minima and maxima, try to relate this word local with this: in some neighborhood. Okay, local neighborhood. You're gonna understand what that means in a moment. On the other hand, global minima and maxima. What is this? Global minima and global maxima are the values of the function which are either a minimum or a maximum for all the domain of f. Now here's the key phrase: for all the domain of f. They are absolute minima or maxima for the function. Okay, so again, I want your mind to match this word global with absolute. Okay, global, absolute, local, neighborhood. This looks like one of those tests. Okay, that they want you to, I don't know, match concepts. Local, neighborhood, and global, absolute. Absolute. You're gonna understand what I mean in a moment when I give you the examples. Okay, local, neighborhood, global, minima and maxima. Those are absolute minima and maxima. Okay, so this is the theory. Okay, and I know that much understanding was not attained at this point. That's gonna come in the examples which I'm gonna present right now, and you're gonna understand that these concepts are very simple once we look at them. Okay, once we look at them. So let's go. Let's go there. Okay, so again, we're gonna use a web application for graphing. Okay, Desmos. I hope you have been using it. It's a very, very, very good application. It's free, first of all, and it's actually really good. Okay, it's developed by a mathematician, so I encourage you to use this. And again, we're gonna use the TI later. Okay, just give me some time. I already talked to the coordinators, and they told me that it was okay for me to delay the use of the TI. So don't worry about that. Okay, so in here we have 8 functions. Okay, this is the first one, second one. It's taking a lot of time. Third one, and so on. We're gonna analyze 8 functions, and we're gonna analyze all the stuff that I told you about. Okay, which I remind you are 3 concepts: the intercepts, the x-intercept and the y-intercept. Second concept, the symmetry. Again, 2 types of symmetry: symmetry with the y-axis and symmetry with the origin. And finally, the local and global minima and maxima. So let's see what all of that stuff means. It's very simple. Okay, first function, look at this. F of x equals x plus 2. This is the graph of the function. Okay, and let me talk about the intercepts of this function. The intercepts. If we can see, the graph of the function goes like in this direction. Okay, it's coming, and it's crossing the y-axis. Can you see at this point? That point, okay, that precise point, and it's coming down, and it crosses now the x-axis. Okay, and they are labeled right now. Okay, so we say the following: this graph has as x-intercept the number -2. This is the x-intercept of this graph of this function, and the y-intercept is 2. Okay, so that's it, guys. It's very simple. Visually, it's very, very simple to get the intercepts. Extremely simple to get the intercepts. Okay, next, another function. This function is this one: f of x equals x squared minus 4x plus 6. Look at the function. Okay, it's coming this way, it's crossing the y-axis at this point. Let me label it. There you have it. Okay, and it's coming down, it reaches a bottom, and then it goes up and up and up and up and up and up until infinity. Okay, so let's talk about the intercepts of this function. Okay, let's talk first about the x-intercept. But wait, the graph of the function is not crossing the x-axis. Can you see? Nowhere, because the bottom of this function is right here, and then it goes up again. It never goes down enough to cross the x-axis. Okay, so what are we gonna say? Well, we're gonna say that this function, this particular function, does not have any x-intercept. Okay, does not have an x-intercept. Don't say that it's 0, okay, because that would be wrong. No, this function does not have an x-intercept because it doesn't cross the x-axis. Okay, now on the other hand, this function does have a y-intercept, which is this one. Okay, it's the number 6. This is the y-intercept of this function. Got it? Very simple things, extremely simple. Next, okay, this is similar to the one before. Can you see? It's also a quadratic function, but look at this. What is the difference? Now we do have x-intercepts. This one, okay? So we have as x-intercepts for this function, we have the number 1, that is the first x-intercept, and the number 3, that is the second x-intercept. And as y-intercepts, we have this one, the number 3. Okay? So any function can either have many x-intercepts or none, okay? And the same for the y-intercept. Only a little caveat, only that a function cannot have more than one y-intercept. It can have many x-intercepts or none. Again, many x-intercepts or none. And as for the y-intercepts, it can have either one or none, but just one. This cannot happen with a function. These two things, okay? Like having two intercepts for a function, for two y-intercepts, that would be incorrect. Okay, that would be incorrect. Now, in the activity, I'm asking you why this is impossible. Why is it impossible for a function to have more than one y-intercept? Okay, higher thinking reactive. You need to think about that. I'm not gonna tell you. I could tell you, but I'm not gonna. So I want you to think. Okay, so that's for the intercepts. Now let's go with the symmetries. Okay, look at this. Look at this function. This is the y-axis, and look how this part on this side of the y-axis on the left side, and this other part on the right side of the y-axis, if I folded such graph, if this graph was on a sheet of paper, and I could fold that sheet of paper over the y-axis, this branch and this branch, they would coincide, and that means symmetry about the y-axis. Another function symmetrical with the y-axis, this one. Okay, a little more complex function, but as you can see also the y-axis divides the graph of the function in two equal and perfectly matching pieces. Okay, if I folded this function over or about the y-axis, this piece on the left side and this piece on the right side, they would match. And so this is a function which is symmetrical with respect to the y-axis. Now, two functions which are symmetrical with respect to the origin, like I said before. Okay, this one, very basic function, f of x equals x, perhaps one of the most simple functions. Okay, try to imagine first this function, this graph being folded about the y-axis, Try to imagine that. What would you get? You would get this, right? More or less. I'm gonna try to do it straight. You would get this. If you folded this function over the y-axis. Okay, now fold it over the x-axis. This and this folded over the x-axis. Clearly this piece is gonna match now this one, and so you have symmetry with respect to the origin, just like I told you in the video, just like I shown in the video. Okay, this is a little more complex to imagine in the mind, but not that much. Another function which is symmetrical with respect to the origin, this one. Again, try in your mind to fold first about the y-axis. Try to fold that in your mind, or you can actually take pencil and paper and do it. Try to fold about the y-axis. You're gonna get this, more or less. right? You're gonna get this piece and this piece now by folding about the y-axis. Now, if you fold this about the x-axis, you're gonna get that this piece now coincides with this other piece. Sorry about that, but you get the idea, right? They coincide, they match, and therefore this is a function. Therefore, this is a function which is symmetrical with respect to the origin. Now, some functions are not symmetrical with respect to neither, okay? For example, this one, look. This one, f of x equals 2 to the x. This function, if you fold over the y-axis, it's not gonna match, right? This part is not gonna match this part, okay? And if you fold about the y-axis and then about the x-axis, again, you're not gonna get any matching. And try to do that, okay? That's a good experiment. Try to draw it more or less, you know. You don't have to be extremely precise. And try to fold over the y-axis and then over the x-axis, and you won't find any matching. So that's what this means. And a function doesn't have to be symmetrical with respect to anything. Okay, now next I'm gonna show you how we get the intercepts. The intercepts, which I'll remember are these things, and how to find whether a function is symmetrical by not even looking at the graph. Okay, by analysis. By analysis. Which has nothing to do with graphs. It's just you doing numerical approaches or equations and stuff, and you can find the intercepts of a function and also whether that function is symmetrical with respect to the y-axis or with respect to the origin. So wait for that in the second part of this explanation.